We'll look at the effect of leptin on weight loss and weight gain circuit neurons. In a previous video, we looked at the negative feedback loop within which these interactions play a part. So, a weight loss circuit neuron leads, when it is active, to weight loss. What leads to weight loss? Well, an increase in activity would lead to weight loss. A decrease in eating or appetite would lead to weight loss. What else? An increase in metabolic rate. An increase in uncoupler activity. All of these things would lead to weight loss. More calories spent, less calories obtained. So, leptin, remember, is a hormone. And it's a hormone that is generated by fat tissue. The more fat, increase in fat, leads to an increase in leptin, and leptin binds to these receptors on the cell. So is this going to activate this cell to make this a negative feedback loop, or is this going to inhibit the cell to make it a negative feedback loop? Well, increasing in activity, decreasing in eating, increasing metabolic rate, decreasing uncoupler proteins, all of these things lead to a decrease in fat. So then leptin wants to activate weight loss. So it activates, leptin activates weight loss circuit cells. How does it do that? Well, it does it in two ways. It closes a channel, and it opens a channel. You should, at this point in the term, I think, be able to guess what the channel identities are. Which one of these is allowing what ion to move through the membrane. Now, this is a typical cell. It's got the sodium-potassium pump, spending plenty of ATP to do that. So, opening what channel would lead to activity of the cell? Well, remember, activate means depolarize. This cell has to have action potentials. It has to reach threshold. It has to depolarize. So, opening what channel will allow the depolarization of this cell? The answer is sodium. Now, it's also true that closing potassium channels will lead to the depolarization of these cells. Just as in pancreatic beta cells, closure of potassium channels is one of the mechanisms by which depolarization is carried out. Weight gain circuit neurons lead to weight gain when active. So, what would cause weight gain? Decreased activity. Increased eating. What else? A decrease in metabolic rate, of course. Again, leptin is going to interact with these cells because when weight is gained, leptin will bind to this receptor. Now, if these cells' activity, all this activity is going to lead to weight gain. What must leptin do to this cell? Well, leptin, remember, is a signal leading to weight loss. So it's got to slow down the activity of these cells. So it's got to slow down the decrease in activity, or not do that, not do that, not do that. So when leptin binds, you're slowing these things down. Quiet bird! Slowing these down is pretty simply done. It means you have to open a channel. Now, this is the potassium channel. And this leads to the hyperpolarization of these cells, so that they're less likely to get the threshold, they're less likely to have action potentials. Given the mechanisms that we just discussed, the mechanisms by which weight gain circuit cells and weight loss circuit cells are regulated by leptin, read this question. Note the number of action potential spikes. Right? Number of action potentials is seen by how many of these spikes occur. And the membrane potential between spikes. So when the membrane potential isn't moving around, the spaces in between, what is the membrane potential? The dotted line is resting potential in each of these. So the question is, this you'll see better in lecture, this transplanted hypothalamic neurons respond to leptin properly part. But what you can understand right now from this video is which neuron exports potassium as a function of leptin interaction. Leptin participates in our feelings of fullness. So, satiety is another way of saying feeling full. Action potentials make feeling full more likely. And if you have enough action potentials in these particular neurons, you feel full. At this period of time, leptin is being added, but only leptin, to one of these neurons who, when they fire, give the sensation of satiety, of feeling full. You'll notice that leptin added to these cells depolarizes the cells some, but not so much that they reach threshold, not so much that action potentials are seen, showing you that the threshold potential of these cells is quite high compared to, say, the pacemaker cells we've seen or other neurons we're going to see over the course of the term. Much higher than -45, right? Here is another hormone, CCK it's called. It's generated by the gut, by the intestines, when food is coming in. This is a signal, meaning food has arrived. Now, food arriving is a reasonable signal for feeling full. If you have enough of this signal, you ought to feel full. But you'll notice that when leptin and CCK are present at the same time, you're going to have a tremendous number of action potentials when compared either to simply CCK or simply leptin being made available, interacting with the set of cells. What does this mean? Well, CCK is a very temporary signal. Leptin is a rather constant signal. It's important to maintain weight balance. You don't want to eat too much or too often, but you certainly do not want to stop eating no matter what your energy levels are. you need to continue to take up essential nutrients. So leptin does not dictate, does not reduce your desire to eat without eating signals coming in. I apologize for the bird. CCK is that signal that food is coming in. Because leptin is present, in this case, at the same time that CCK is coming in. So CCK is only going to come in while you're eating, and only after you've had some signal that you've eaten will the combined, oh, you've got plenty of energy that leptin indicates, and you've eaten something that CCK indicates, lead to a more profound sense of feeling full, of satiety.